Okay, so in this video we're going to talk about the basic concepts of how circuits work. Just to review a few key concepts, in the last video we talked about the definition of electric current, and we talked about the concept of drift velocity. And so remember that electric current, which has a symbol capital I, is defined as the rate at which charge flows past a point in a given amount of time. Okay, and so that is measured in amperes, where 1 ampere would be 1 coulomb per second. And so the analogy we're going to keep going back to is water flowing through a pipe. And if you imagine water flowing through a pipe, say like the pipe itself is like a wire, and what is moving in a pipe is water. Okay, when you talk about electric current, what is moving is charged particles. Okay, so to take the analogy further, the faster the water flows, okay, that is, the faster the charge flows past a point, the higher the current. Now, what is it that actually causes the flow to happen? Okay, well, in a water pipe, what causes the water to move in a pipe is water pressure. When you talk about current, what causes current is potential difference. Okay, or the other way that we describe potential difference is what's called voltage. And so voltage, which you've probably heard of before, is basically synonymous with potential difference. Okay, so voltage and potential difference are the same thing. So when we say a potential difference is applied on a conductor, that's the same thing as saying there's like a voltage across that conductor. And we know from the last unit that we did last semester that when you have a potential difference, when you have a voltage, that means you have an electric field. Okay, because you have an area where there's a higher potential energy associated with that position in space compared to another position. So that creates an electric field going from high potential to low potential, and we know if there's an electric field, there's going to be an electric force. And so that means if you apply a potential difference of voltage across a conductor, because conductors have free electrons, if those free electrons experience an electric force, they're going to move. And so obviously moving charge constitutes electric current by definition. Okay, and so if current is like the water flowing through the pipe, voltage or potential difference is basically like the pressure in the pipe. It is the thing that is pushing on the water, not physically pushing, I guess, but the thing that actually causes the current to move. All right, so when you talk about a circuit, I'm going to go to the next slide, so pause there if you need to write this down. But when you talk about what constitutes a circuit typically consists of 3 primary elements. Okay, you have to have at least one source of potential difference, okay, one voltage source, and that could be like a battery, or that could be a power station, a power supply, but some source of potential difference, okay, which causes the current to flow. You have to have a closed conducting path, meaning you have to have a path for the charged particles to move along. And you have to have at least one load. And when we talk about a load in a circuit, we're basically talking about what is it that's using up energy. Okay, what are the components that we're trying to power? So for example, when you plug your cell phone in to charge it, your cell phone would be the load. Okay, if you flip a light switch and the light bulb turns on, the light bulb would be the load. And so the load is whatever is using power in your circuit. Okay, if you think of like your house or your apartment, basically everything plugged into the wall outlet is part of a big circuit, and so everything in your house constitutes like one big load acting on the power supply to your house. Okay, so how does a circuit work? Well, it all relies on that source of potential difference, that voltage source. Okay, and this little animation here is meant to kind of help you understand how the voltage causes the charge to move. Okay, and so the idea is that you have a voltage source where one side of the voltage source has a higher potential than the other side, and the voltage source kind of acts like a pump mechanism. And when I talk about like a voltage source, think like a battery. Okay, a battery has a positive side and a negative side. Okay, the positive side of a battery has a higher potential than the negative side. Okay, that's how that works. Now what happens is the voltage source basically lifts the positive charge up to a higher potential. Here it's kind of analogized as like an escalator. And then what happens is you have positive charge at a higher potential. And we all know if you have positive charge at a higher potential, it wants to go back down to a lower potential. And so it's going to keep on moving, trying to find its way back to a lower potential. And in doing so, that energy that that positive charge loses, like right here, you can see the positive charge going from high potential to low potential across the green powder wheel. That energy has to be used up. Okay, and so in this case, it's used up in the load. So in this animation here, the green powder wheel would be like the load, and then the left side over here where it says battery/pump, that would be the voltage source. Okay, and notice you have a closed conducting path that the charged particles keep going kind of like in a loop. Okay, they go up in potential because of the voltage source. They try to fall back down. They go across the load. There's what we call a voltage drop, where that charge is not disappearing, but it's basically giving its energy up to the load. And so once it ends up back at a lower potential, it keeps moving across the voltage source, gets lifted back up to a higher potential, and then the whole process keeps on repeating. Okay, so notice that the charged particles keep moving. None of the charged particles disappear. None of them get used up. It's the same amount of charged particles making up the current. Okay, what does get used up, though, like I said, is the energy that the charged particles have. As the charged particles go from a high potential to a low potential, they go down in energy, and that energy is used up across the load. Okay, so for example, if this green powder wheel was like a light bulb, okay, the charge going from high potential to low potential, that charged particle loses energy, and that energy appears in the light bulb in the form of light, right? And so that's basically how a circuit works. Okay, so the voltage source acts as a pump mechanism, and once the charged particles end up at a higher potential, they try to seek out a lower potential, and the process repeats itself. Now, before I move on, I want to point out something important. You might have noticed that in this animation and in my talking about this animation, I refer to the voltage source lifting these positive charged particles up to a higher potential, and then the positive charged particles go back down to a lower potential. Okay, and you might be a little confused because previously we've been talking about how free electrons move in a conductor, and it's the free electrons that cause a current to flow, and electrons don't have a positive charge, they have a negative charge. Okay, and so there's something kind of weird about the way we define the direction of electric current. And the reason for that is kind of due to historical reasons. But by convention in physics, and I think it's different in chemistry, but in physics, we define the direction of the electric current to be the direction that positive charge flows in a circuit. Okay, so if I say the current is going to the left, that indicates that positive charge is moving to the left. Now, the only issue with that is that we now know that in most circuits, that's not actually what happens, because in most circuits you have conductors, and conductors have free electrons, and it's the electrons that are actually moving. Okay, the issue is that that this convention was defined way before we even knew electrons existed. Okay, in fact, that goes back to like Benjamin Franklin. Basically, he had a 50-50 shot of defining what positive charge was, and he chose wrong. And so now we're stuck with this word convention, where we say the current is going whichever way positive charge is moving, even though it's not actually positive charge moving in most circuits. Okay, so it's not really that big of a deal, because if you had positive charge moving to the left, mathematically speaking, that's the same thing as negative charge moving to the right. And in most situations, it doesn't really affect anything. It's just something to kind of keep in the back of your mind. We're going to be talking about, the current is going this way, the current is going that way. Talking about positive charge, just remember that that's not actually what's happening like in real life. It's just that's the convention that we're kind of stuck with. Okay, so just kind of keep that in mind. Okay, and I think I've talked about all of this stuff before. I don't think there's anything new in here. We already talked about the voltage source, the battery acting kind of like a pump mechanism to lift the positive charge up to a higher potential. I would show you another animation here, but this one isn't working. Okay, so I want you to pause here and see if you can't answer this very basic and intuitive question. Using your intuition, how do you think the current in a simple circuit would react to a higher voltage source? So see if you can figure that out. Okay, well, this should be pretty common sense, but since voltage is what is pushing the current along in a circuit, the more voltage you have, the more current you have. Okay, that's, again, pretty intuitive. It turns out in a lot of situations, there's actually a more specific relationship between current and voltage that we'll see in a couple minutes or later on. Okay, so before we talk about that, I also want to tell you that a voltage source lifts positive charge up to a higher potential. Then there's what we call a voltage drop. We're going to use that term a lot later on. A voltage drop going across each component along the circuit as the positive charge carriers flow from a higher potential to a lower potential. Okay, when I talk about a voltage drop, what I mean is what I showed you this in the animation before, but when you see the positive charge here going from high potential, then it crosses the green paddle wheel and it ends up at a lower potential. That is what we call a voltage drop. Okay, and the name is self-explanatory. It's literally dropping in potential. Okay, so we'll see that terminology used a lot later on. For right now, we're going to discuss one more key quantity to dealing with circuits, and that is the concept of electric resistance. I say this all the time, but please do not forget that definitions are important. Okay, there's a difference between knowing what something means and knowing what the definition is, and so you need to know both of those things. Okay, here's the definition of electric resistance. The electric resistance of an object is defined as the ratio of potential difference across that object to the amount of current that flows through that object. Now, intuitively, resistance basically just measures how easy it is for current to flow through something. Okay, that's not the same thing as the definition. This is the definition. Okay, it's important that you understand definitions because sometimes you have to answer definition questions on the IB exam. Kind of like how if I ask you, what does temperature means? If you tell me temperature is how hot or cold something is, that's true, but that's not the definition of temperature, because the definition of temperature is a measure of the average kinetic energy of the particles making up an object. Okay, so there's a difference between understanding what something means and knowing the definition. Okay, so make sure you understand the definition of electric resistance. So basically, if you took any object, okay, you measure the potential difference, you measure the voltage across that object, you measure the current going through that object, and divide those two numbers, because a ratio means you're dividing, that ratio is defined to be resistance. Okay, and so I could write that as just R equals V over I, where here V is a symbol for voltage or potential difference. Now, in topic 5.1, we wrote potential difference with a delta V. When you're dealing with circuits, it's typical to write just a V and not a delta V because the V is understood to be potential difference, not potential difference. Okay, even though really it would be more accurate to put it with the delta. People who do stuff with circuits don't have time for all that, so usually they just put a V, understanding that V means potential difference. Okay, so I'm just going to write a V, just kind of keep in the back of your mind that it's not like one specific potential, it is a potential difference, it is a voltage. Okay, so this is how resistance is defined. Electric resistance is a scalar, meaning it has magnitude but not direction, and the unit of resistance is the ohm. Okay, it is given the Greek letter omega. This is an uppercase omega. You can see it right here. Not to be confused with the lowercase omega, which might be the symbol for like angular frequency or angular velocity. Okay, so this is an uppercase omega. It kind of looks like a horseshoe, and that is the unit for resistance. Okay, so make sure you understand what resistance is. Okay, so moving on. Okay, this chart right here just kind of summarizes the three main quantities we've talked about. These three things, voltage, current, and resistance, those are the three main quantities in circuits. Okay, and then this is just like a cute little picture showing you, like, voltage is what's making the current go through. So here you can see the volt is trying to kick the ampere through the wire, and then the ohm, the resistance, is what's like stopping the current from flowing. Okay, so that's just like a cute little cartoon. I do want to show you, this is topic 5.2. In the IB data booklet, you are given the equation that defines resistance R equals V over I. Okay, so that is given to you. Okay, so just to give you a really basic example, a potential difference of 1.5 volts is measured across the light bulb in a circuit. The light bulb is known to have a resistance of 100 ohms. Calculate the current that must be flowing through this light bulb. Okay, so R equals V over I. We have V. Okay, V equals 1.5 volts. We have the resistance is 100 ohms. And so it's just basic algebra to rearrange this and get I by itself. So we have 100 equals 1.5 divided by I. So that means I is 1.5 divided by 100, which is 0.015 amperes. Okay, so just really basic example using the definition of resistance. Okay, now a few minutes ago I asked you the intuitive question, what would happen if you had like a higher voltage source? How would that affect the current? And hopefully you said more voltage means more current, which is very intuitive and makes complete sense. But there's not just like a positive correlation between voltage and current. In some situations, in many situations, there's a specific type of relationship. Okay, and that relationship comes out in what is called Ohm's law. Okay, so pause here, make sure you add this to your notes. Again, I will tell you that definitions are important. Okay, here's what Ohm's law says. Okay, and notice, by the way, Ohm's law applies not in every single situation. It just so happens, experimentally speaking, that Ohm's law just happens to apply for many different materials. Okay, Ohm's law says that the potential difference across a component is proportional to the current through that component at a constant temperature. Okay, the potential difference across a component is proportional to the current through that component at a constant temperature. The constant temperature part is important for the definition. Here's what that means. Okay, we've seen that word proportional before. A proportional relationship means that you have a variable is equal to a constant times, a variable is equal to another variable times a constant. Okay, so in other words, V is equal to I times a constant. Well, the only way that Ohm's law works is if R is constant. Okay, so Ohm's law is equivalent to saying that the resistance of a material is constant for a given temperature. Now, that's not true in every single situation. There's many situations, many types of materials, or many types of components where if the temperature changes, the resist, or I shouldn't talk about temperature, but there's many situations where, let's say, if you double the voltage, the current like quadruples or something weird like that. Okay, it's not necessarily like a proportional relationship. Okay, or there's many situations where, as the temperature changes, the resistance also changes. Okay, if you have an object where Ohm's law applies, that means R is constant for a given temperature. Okay, and if you have an object that meets that criteria, that obeys Ohm's law, we call that an ohmic material. Okay, so if it obeys Ohm's law, it is ohmic. Okay, that means if the resistance does not change, even with different voltages, we say that material is ohmic. Okay, again, what I mean is if we like apply 2 volts to something, we measure the current. If we make it 4 volts, the current should also double. Okay, so it should be a proportional relationship. Okay, and so if that's the case, it's an ohmic material. If it's non-ohmic, then the resistance does not change proportionally for different voltages. Or I should say, sorry, if the current does not change proportionally for different voltages, we say the material is non-ohmic. Okay, and so let's see. Okay, just go ahead and pause it here. Add this to your notes. On the last slide, we talked about how electric resistance is defined. We talked about the conceptual understanding of resistance, basically how easy it is for current to pass through something. Materials that have a low resistance, like conductors, current passes very easily through them. Materials with a high resistance, like insulators, tend to pass very little current through them. We also talked about Ohm's law, which basically says that for a given temperature, the resistance across an object is constant, meaning we have V is equal to I times R, and we're treating R as a constant, and this is what's called Ohm's law. Ohm's law is not a theoretical law. It's not like Newton's laws of motion or anything like that. It just so happens that people have done experiments with many different types of materials, and it just so happens that this relationship seems to be true for many different types of materials. Okay, so it's experimentally true. It's not like, theoretically derived from some like deeper concepts or whatever. It's something that happens to be the case when we do experiments. Most of the time when we're doing problems in class or we're dealing with materials in class, we're dealing with ohmic materials. Some real-world materials are non-ohmic. The one that you need to be most familiar with is a filament light bulb. This is one of those like old-fashioned light bulbs that basically works by, it has like a little piece of metal in it that's called the filament, and when you turn on the light switch, current runs through that little piece of metal and it heats up the metal and it glows. Okay, and so this is most light bulbs were like filament light bulbs like 10, 20, 30 years ago. Okay, nowadays we have like LEDs and stuff like that. Okay, but an older light bulb is like a filament light bulb. That is considered by the IB to be a non-ohmic material. And there's some other examples of non-ohmic materials that we'll talk about later. But most of the time we're dealing with ohmic materials in this class. I also want to point out Ohm's law only applies if the temperature is constant. In real life, the resistance of a material actually depends on temperature. And the reason electrical resistance depends on temperature is because, remember, temperature, I said this before, is a measure, by definition, is a measure of the average kinetic energy of the atoms or molecules making up an object. Okay, so think about if you increase the temperature of a metal, that basically means the atoms in the metal and the free electrons in the metal are going to start to vibrate faster. They're going to shake in place faster. Okay, in order to have a current flowing through a conductor, you have to have moving charge. But what happens is, let's say you have like a wire and you have electrons flowing through a wire. If the temperature gets higher, then those electrons that are trying to move along through the wire, they tend to collide with stuff more often. They tend to collide with other electrons, or they tend to collide with other atoms more often because those other atoms are like vibrating faster. And so if they're vibrating faster, it causes like more traffic for those electrons to move. And so for most materials, higher temperature means higher resistance. Okay, that's not true 100% of the time, but in most situations, more temperature means more resistance. Okay, let's see. I already talked about Ohm's law. That's Ohm. He was a German physicist. He did stuff with electricity in the early 1800s. This is how he wrote his law. I think we already talked about that. By the way, keep in mind the time frame. He wrote this in 1826. J.J. Thomson didn't even discover the electron until like the 1890s, right? And so, again, it kind of makes sense that because we didn't know what exactly was moving with regards to the electric current, it kind of makes sense that somebody could have messed up the convention for the direction of current, which was done by Benjamin Franklin, like I said before. Okay, so life is hard sometimes. If you were to take an object and, let's say, make what's called a VI graph of that object. Okay, a VI graph basically just means take an object, you apply a voltage, and you measure the current. And then you change the voltage and you measure the current again. And then you change the current, you change the voltage and you measure the current again. And if you keep doing that enough, you can get a graph. You can make a graph. Okay, well, if you have an object that is ohmic, that graph is going to be linear, because if V is proportional to I, that graph is going to be a linear graph going through the origin. Okay, so notice this middle graph here would represent the VI graph for an ohmic material versus the first graph and the third graph, which are very obviously non-ohmic. And so sometimes you're asked to solve problems given a graph of voltage and current, a VI graph. Okay, this is basically, again, just showing you examples of different voltage current graphs and how, A is obviously showing an object that's ohmic. B is a VI graph for a non-ohmic light bulb. C is a diode, and D is a thermistor, which we'll talk more about thermistor later on. Okay, and I just want to do a quick example. Take a look at this example here. We're given a VI graph. For some reason, they gave us the answers before giving us a graph. That's fine. But this is an IB question. And it basically says the graph shows the applied voltage V versus resulting current I through a tungsten filament lamp. Find R when I equals 0.5 milliamps and 1.5 milliamps. Is this filament ohmic or non-ohmic? Okay, so the first part of the question basically just requires you to know the definition of resistance. Okay, R is the potential difference across an object divided by the current flowing through that object. So if we want to find R when the current is 0.5 milliamps, all we need to do is go to the graph, find 0.5 milliamps right there, use the graph to find the voltage, and then divide. Okay, which you can already see the solution here. Okay, so the voltage there comes out to be about 0.08 volts. The current, 0.5 milliamps, if you convert that to ampere, remember milli is 10 to the negative 3. So if you just divide V divided by I, you get 160 ohms. So this is the resistance at 0.5 milliamps. Now, if we're asked, is the filament ohmic or non-ohmic? If it was ohmic, you would expect that resistance to always be the same no matter what the current was or no matter what the voltage was. Okay, you would expect that ratio to stay the same. But if you actually use the graph to find R at 1.5 milliamps, again, you go to the graph, you find 1.5 milliamps, you go up, you go over, you find that 0.6 volts, you do 0.6 volts divided by 1.5 milliamps, you get 400 ohms. Okay, well, obviously 400 ohms is not the same as 160 ohms. Okay, if the resistance wasn't constant, that means this is non-ohmic. And of course, you could probably tell it was non-ohmic from the graph because, if it was ohmic, the graph would be linear going through the origin, like we talked about before. Okay, so you should definitely be able to find electrical resistance given a VI curve for a given object. Okay, let's see. I think we've talked about this before. I don't think there's anything new there. Just really quickly, I want you to take a look at a question. This question was on the IB exam just a couple of years ago, so this is a pretty recent question. And this is one of those questions where, this is why I always say definitions are important. The question says, which of the following is a statement of Ohm's law? Okay, so see if you can figure out the answer to this question. Okay, so the answer to this question is C. The resistance of a conductor is constant provided that the temperature is constant. Okay, A is not true. A is partially true, but you have to have that constant temperature piece to completely be a statement of Ohm's law. B, people might put B because, they're like, oh, it's the longest answer, and plus it does talk about the temperature being constant. But if you read it carefully, it says the current in the conductor is inversely proportional to the potential difference. It is not inversely proportional, it is just directly proportional. Okay, inversely proportional would mean that more potential difference means a smaller current. Okay, that's not the case here. Here, more potential difference means more current. So an inverse relationship, let's see, inverse would be like, I equals R divided by V, when actually it should be I is equal to V over R. This is an inverse relationship. This is a proportional relationship. Okay, so B is out. And D says the current in the conductor is proportional to the potential difference across it. That is basically the same thing as A. It is mostly correct, but it's still missing the constant temperature piece. Okay, so the correct answer to that question is C. Okay, so hopefully after watching this video, you have a better understanding of the basic idea behind how circuits work. In the next video, we'll talk more about power dissipation, and we'll start looking at circuit diagrams and get to doing more calculations with circuits. As always, please let me know if you have any questions, and I'll see you guys in the next video.